So happy to see that. So I think that your work is paying off. I see a lot of progress in Alex. I'm pretty happy about that. Here is the test. Okay. And so, yeah, exactly. Get your snapshot. So what I'll do is I'll just kind of walk you through the number and types of problems because 77 topics doesn't fit into 33 questions, right? And so let me help you narrow your target for what you're going to study, okay? These are some of the more important ones that I think we covered. So I've got three. The first three problems are just straight up unit conversions. So using like the metric system or, using, canceling this unit with that unit and so on. I think it's important that you know how to handle like a square or a cube, right? So if it's like cubic meters and you need to figure out how to get to say cubic centimeters, right? Centi is 10 to the minus 2, and so you need to figure out how to get from say cubic meters to cubic centimeters, okay? And we can do some of these afterwards to just help you review, okay? There's three of those just straight up unit conversion type problems. A couple of them on the unit like metric system prefixes. So go back through and learn at least like the middle six, right? From like mega to micro. Have those memorized. Then there's three temperature conversions. So going from Celsius to Kelvin and Kelvin to Fahrenheit and Celsius to Fahrenheit. Okay, so you need to know those. Got a couple of problems on like a homogeneous, heterogeneous mixture, because I think that's important too in chemistry to understand the language of mixtures and solutions. Which is a solution? A heterogeneous mixture or a homogeneous mixture? Homogeneous. Homogeneous mixture and solution are the same thing. Okay. So just two words for the same thing. Homogeneous is a solution. Okay. Sig figs. Okay, 1, 2, 3, 4. So I have 4 problems on sig figs. Okay, one, just straight up identifying how many sig figs there are. That's sort of the lowest level problem. Here's a number, how many sig figs. And then here's an addition, how many sig figs. Here's a multiplication, how many sig figs. And then a combination of addition and multiplication. So you see how it kind of ramps up in difficulty. The real easy one, up to the hardest sig fig one where you have a combination of addition and multiplication. So review that. We can do a problem on that in a minute. Okay. Then we get into more chemistry topics like density. I put a couple of problems on density because that's an important concept. Okay. It will do you a lot of good if you memorize the density of water. Do you know what the density of water is? It's a pretty easy number. It's 1, but 1 what? 1 gram per mil, or 1 gram per cubic centimeter. A cubic centimeter and a milliliter are the same thing. So 1 gram per milliliter is the density of water. And that's just something that as a scientist, or even someone even close to science, ought to know, okay? So why does wood float? It's less dense than water. So think about a volume of wood. If you push a volume of wood underwater, it displaces that volume. If it weighs less than the water it pushed out, the water is going to fight back. Okay? And so gravity is affecting everything. And so that's this balance of gravity. If the wood or the ship or the whatever is displacing water, and that's how they measure ships. They talk about, and not weight, they talk about displacement of water, because that's going to balance. That ship's going to go down until the weight of the buoyancy of the ship, the weight that's underwater, balances with the density of water. Okay. So if something's more dense than water, what does it do? It sinks. Okay, so basic stuff. And then there's just simple calculation using density. What is the equation for density? Mass over volume. That's right. So mass on top, volume on bottom, that's the density. Okay. Okay. So those are your two density problems. And again, this is being recorded, so you know, you can scribble your notes and that's good, but you can also go back to the video. I'm going to post it after class. All right, then I get into this atomic notation. Yes?
How many questions are on the exam?
33. So they're 3 points apiece. Yeah. And we get into this notation for atoms and things, like we might have, let's see, like carbon, 6, 12, right? And I ask you a bunch of questions on that. So 1, 2, 3, 4, 5, 6-ish. 6 questions kind of about atoms. Okay? So I look at that carbon 12, that's the isotope, carbon 12, right? There's also a carbon 13. What's the difference between carbon 12 and carbon 13? Different number of what? Neutrons, yeah. And also different number of particles in the nucleus. How many particles are in the nucleus of a carbon 12? How many particles total? 12, yeah. So the particles in the nucleus are neutrons and protons, and that 12 is the sum of all of them. So all of the particles in the nucleus add up to 12. How many protons? 6. And so then by difference, how many neutrons? 6. Yeah. So those are easy questions if you know what the notation means. So boom, 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 3 points, 3 points, 3 points. Those are great. Okay. So how many electrons in a neutral carbon 12? Right, because it's neutral. The electrons match the protons, and so you know how many neutrons. But this is all basic stuff. So I don't want to just test you on the hard stuff. I want to test you on the basic stuff too. And so then later when I'm looking at the exams and you're like, I've studied really hard, and I'm looking and I was like, you don't even know how many neutrons are in the nucleus. You know, maybe you missed that, but I told you today, study that so that it's basic knowledge. So, and those are definitely easy questions to get. Now, we get into the ISO things like isoprotonic, isoneutronic, isoelectronic. What does all that mean? What's the ISO word mean? Same. So if I wanted to come up with an element that was, let's say, trying to pick an easy one. Let's say, what could I write that was isoprotonic with carbon 12? Isoprotonic. It would have to be carbon because protons define what the element is. So it would be some other kind of carbon. So it would be carbon. That's isoprotonic. But it can't be carbon 12. What could it be? Carbon 13 or carbon 14. Yeah. Let's do carbon 14, like carbon 14 dating, right? So that would be isoprotonic with carbon 12. And those would be isotopes. So same type of element. That's where the word tope comes from, tope or type. I think some, over time language changes a little bit. And so isotope you can think of as isotype, same type of element, different number of neutrons. Okay. It got real quiet. Is this something that y'all are worried about? Or is it's just you weren't expecting? Yeah, that's like making a mental note. Yeah, okay, good.
Oh, so can we clarify? So the 6 on the bottom of so carbon 12, 6, carbon 14, 6, the 6 is the proton.
Yes.
It goes to the bottom.
Yeah, so the protons, and that's why we omit it a lot of times. Because if I say carbon, it's got to have 6 protons.
Okay.
Yeah.
And that's just understood.
Understood. Yeah. And so a lot of times you'll see it written like this. You'll just see carbon 12 and carbon 14. Because the 6 is obvious because it's a C. Yeah.
In this format, will it ever have the electron notation on that as well? Or
That would be shown as a charge.
okay.
And so, yeah, if it was, so let's do carbon 12, like 4 minus. Or just do minus, 4 minus, right? Okay, so carbon 12, 4 minus. That is a. Can you see that?
Yes.
Okay. All right, great. Now, how many electrons does that atom have? 10. So a neutral carbon has 6 because there's 6 protons, 6 electrons. And so if I add 4 more electrons to the cloud, I have 10 electrons. Okay? And is that a happy carbon atom? I mean, it's got a lot of negatives, but what makes it happy?
The valence.
It's got the same number as neon, and neon's a noble gas. So noble gases are awesome. They have a very stable electron cloud. And so the carbon 4 minus, listen very carefully to this, carbon 4 minus is isoelectronic with neon. Same number of electrons, isoelectronic. So know that word as well. So all the isos, isoprotonic, isoneutronic, isotope, and isoelectronic. Those are really good vocabulary words. And that's what separates you as a scientist from your peers who never say anything specific or technical. Everything is stuff. Everything is like this or like that. But a scientist speaks specifically. They use the technical terms like isoelectronic, isoprotonic. So don't be afraid to use the technical language. That's what starts to grow you as a scientist. And it also changes the way you think. When you're specific in your language, you'll be more specific in your thinking. So I can't test you individually on that. Because I want to get your grades back quickly, I do my multiple choice test. But I wish I could sit down with every one of you individually and interview you and like evaluate your language and how you're using technical language. Start speaking technically in appropriate situations. Don't just like bring it up at lunch. Well, such and such. Don't be an idiot. But in terms of when you're speaking on a scientific topic, use the technical language. It'll like I said, it'll change the way you think. Then I get into the families. There's 2 questions on the families of the elements. I could ask more, but again, it starts to add too much weight to that. It's more like it's useful, but it's sort of all or nothing. So I've got two questions on like alkali metals, alkaline earth. What are the pnictogens? What group is that? It starts with a P, but it says, yeah, it's the nitrogen one. So it's PNIC, pnictogen, and it's the nitrogen group. So it sounds to me like somebody just mispronounced nitrogen and spelled it weird, right? So you see PNICTOGEN, that's a pnictogen, that's a nitrogen group. Oxygen that group is what? Chalcogens. Then the one you see all the time, the fluorine group, the halogens, yeah, and then the noble gases.
So would a fluorescent light be the halogen light?
A fluorescent light, it uses a lot of different things. These lights actually use mercury, okay? Fluorescence is the process of how it emits light, yeah. But like a neon light, there's neon lights that are red typically, but you have other lights that are called neon lights, but they use other gases. Like the blue ones are argon, and the purplish blue are like xenon. So they use different noble gases for those, and maybe even mix in some of the other elements. But noble gases were the first kind of fluorescent lights, like the bright red neon lights. Yeah. Then we realized we could use mercury, and mercury spits out a red photon, a green photon, and a blue photon, so it appears to us to be white. And so it produces nice bright white light, even though it's toxic. And so there's just a very little amount of mercury in there, enough to make the bulbs efficient, but don't break them, okay? Because there's a bit of mercury vapor in there, and so you don't want to be exposed. Okay, a question on empirical formulas, where you take the structural formula, the formula, and like simplify it. So review a little bit on empirical formulas.
One of those?
Yes. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So a third of the test is naming, because that's the vocabulary of chemistry. If you don't know that H3PO4 is phosphoric acid, almost screwed it up, phosphoric acid, then you're lost later, right? So I give you an acid-base problem, and I say phosphoric acid is neutralized with such and such molar solution of sodium hydroxide, and you're still wondering, wait a minute, I don't know what chemicals I'm talking about. That's a huge problem. So a third of this test is naming. Chemical structure to or formula to the name, and chemical name to the formula. Back and forth. Acids, hydrates, ionic compounds, molecular compounds. So there's a couple of molecular compounds. It's kind of well distributed. There's 1, 2, 3. Three that are acids. Three that are just like ionic compounds. There's a couple of the non-ionic ones, the covalent ones, where you use the mono, di, tri, tetra, and a couple of hydrates and a couple of the like dihydrogen phosphate or hydrogen sulfate or hydrogen carbonate ones. Okay. Yes.
So I have made myself flashcards.
Yes.
And so some of those that are like the dihydrogens, they also have like secondary names.
Like bicarbonate and bisulfate. I'm
And
not
like the
testing you on the old
bisulfate.
ones. Yeah.
Okay.
It's great to see them and great to know them, but I'm not testing you on them. I'm testing you on the like technical names, and I will use those in my problems in my tests. Like I wouldn't say bicarbonate, but I would say hydrogen carbonate. Yeah, yeah. And that's the test. Yeah. So of the things I talked about, now let's efficiently use our time. So if you have a question on sig figs or a question on density or something like that, then we can work on your problems. Yeah. The more specific the question, the faster we'll go. Like, so instead of saying, can you do a problem with density? Try to drill down and say, okay, I don't understand how to use density as a conversion factor or something like that. Like if you can try to drill it down to the thing that confuses you, then we'll really make some headway. So I didn't plan anything for today except sort of tell you what the test is like and then take your questions. The unit conversions are all sort of the, like say grams per milliliter, and you're converting it to kilograms, right? So there's 1,000 grams in a kilogram. So you're just, putting 1,000 on the bottom, canceling the grams, and you're converted to kilograms.
Like the milliliters if you're just trying to get the kilograms?
No, it just would then be in kilograms per milliliter. Yeah.
So to piggyback on that, when we're doing the conversions or when we have to do the like adding and then doing like multiplication and stuff, how does that affect the sig figs? That's how I always get mixed up on that.
Yeah, okay, so let's just do one of those. Okay, so the question was, and I'm gonna sit down for this. It's not great video, but I wanna make sure my handwriting is clear. So let's just do 1, 2, 3.4567. And I'm gonna subtract subtract 0.02 0, okay? So you're talking about how does it affect the sig fig. So this is subtraction, and so first of all, let me underline the sig figs, right? In this first one, everything's significant, correct? All non-zero. What about the second one?
Just the 2 and the trailing.
The trailing 0, yeah. So right there. So I know that right here is the place value of my uncertainty. Okay, so I'm going to go ahead and do the full subtraction. I'm going to subtract, bring the 7 down. 6 minus 0 is 6. 5 minus 2 is 3. I've got a 4, a decimal place, 1, 2, 3. Okay, so that's my result. But this place value right here in the third decimal place, that's where I'm uncertain in my second number. So that kind of wrecks my precision a little bit, right? And so that makes me have to round right here. So I would round this to 123.437. And that would be the rounding. And so we don't count sig figs when we do addition and subtraction, we count place value. So we're looking at that third decimal place, that's where we round. Okay. So even though the second number had only two significant figures, it doesn't cause me to round the result to two significant figures. I would have to do that if I multiplied. If I'm subtracting, then it just tells me where to round. I round at that third place. Okay. So did that answer your question? Yes.
What if there's a problem that you have to subtract and then also multiply?
Yeah, so then if I multiplied this by, let's do this. This will be interesting. So 123.4567 times 0.020. Okay, so same kind of scenario, except now I count significant figures. Okay. So I hate to double all these numbers, but that's what we got to do, right? All right. So, someone quickly, just because I want to be fast, someone type that in your calculator real quick. Two point something? Yeah.
0.4.
Okay. Are you doing it in scientific notation or? Yeah, okay, 2.4. Yeah, because it's 0.02. Okay, 2.4. Keep going. 6, 9, 1, 3, 4. Okay, so that's before rounding. And now this right here only has two significant figures. And so I round to two significant figures. So this would be 2.5. Dramatically different.
So if we needed to do that in the same problem, like both of these combined
Yes.
together, would we wait to round the sig figs till the end?
Yes, so this is what we would do. So if we had, let's just make it, y equals 123.4567 minus 0.020 in parentheses times 0.020. Okay, you see what we would have here. And so we would end up with this result right here times the 0.020, which would round to 2.5. So this piece right here, we would do first, right? If you're doing this math yourself, you're going to do the subtraction first, and then you're going to multiply. You do the sig figs first for the subtraction, and then multiply. So this would be the 123.437. Okay. And then times the 0.020, which again, this uncertainty is way down here, but we're only going to have two significant figures, and so that's going to be the 2.469 ... and that would round to 2.5.
And if it was, instead of 0.20, if it was 0.020, instead of it was, let's say, 0.022, that's still only two sig figs, right?
Correct. Yeah, and you would just do the math,
So you
and then
count-
yeah.
If it's 0.020, the 0 after the 2 counts in the significant.
Yeah, so trailing zeros always count. Yeah, because they're telling you about the precision. Think about it. Yeah, if you're measuring something really precisely and it just happens to be zeros, that's okay. You're still measuring out to that distance. Yes.
And then if it's just a whole number, you would have to do you would go based off the other number. Whole numbers wouldn't count as a sig fig.
Like a counting number?
Yeah.
Yeah, so counting numbers don't restrict your significant digits. So if we were taking this number and dividing by 3, because we're cutting something in a third. We're cutting it in exactly 3 pieces. So we wouldn't count that 3 as a single significant figure. We would divide by 3 and then use the sig figs for the original number to round. Yes.
And then also, would it be, like, if it was 0.202, that would be 3 significant.
Correct.
Right?
Yes. So that would be what we call a captured 0. So zeros in the middle are also significant. The only zeros that are not significant are the leading zeros, the 0.020. So the first 2 zeros are not significant. All they're doing is telling you where the decimal place is. And so you can always sort of check yourself. If you were to write that number in scientific notation, you wouldn't do anything with those initial zeros, right? If I was to write that number in scientific notation, it would be 2.0 times 10 to the negative 2. I used the leading zeros to tell me where the power of 10 was, but they're not significant. Yeah. Great. Okay. What family of elements is cesium in? You got to know what cesium is. CS. Where's CS?
Alkaline
Alkali
metal.
metals. Okay. What type of cation or anion does it form? Cation plus 1. Yeah. Because that whole column, the first column. Yeah. Okay. Fluoride. Where is that? What fluorine? What? Yeah. -1. Halogen. Yeah. Yeah. Good. So cesium fluoride would be CSF. That's right. Do I need a Roman numeral for cesium? No, because it's in the first group, that first column. What about iron? Do I need a Roman numeral for iron? Yes. Yeah, what are the 2 common ones for iron? 2 and 3. 2 and 3, yeah. I don't ever, I like try to stay away. I won't say I won't ever because I might make a mistake, but I will not intentionally make you guess which iron to use. You know, like I'm going to give you a compound that you could figure out which iron it is. Or if I give you a name, it's going to say iron 3, such and such, and you give me the formula, right? So I'm too nice to you on that. Yes?
And so specifically for iron, when we're naming that, in like, not in like a scientific notation, like not the chemical formula, but
Yeah.
like writing it out.
Right.
Are we ever going to use like ferric and ferrous?
No, those again are old names.
Okay.
Right.
My last teacher was old school, I guess.
Yeah, and that's fine. I mean, it's kind of the argument for requiring that is because you're going to find an old bottle on the shelf someday and it'll say ferric chloride. You're like, ferric chloride? What is ferric? You know, so, but I don't know. That's what Google's for.
Yeah.
Right? So, yeah.
A good scientist should know whenever it's like, oh, let me make sure.
Yeah, let's double
Yeah,
check.
let's
That's
double
right. Yeah, let me
check.
double check. And then I'm sure they're like, no, you weakling, you know. But I mean, it's like drinking from a fire hose in this course anyway. And so I'm trying to like give you a path through it that is achievable, and you can always add those little extra things on as you go.
On the exam, will there be like any like conversions using density?
Yeah, so if you wanted to, let's just do one of those. So, let's see. Let's say we have a boat. Weighs 10,000 pounds. How many gallons does it displace? Okay, so this is a tricky one because I'm talking pounds and gallons. Okay, now you don't have to memorize those numbers. I give them to you. Okay, so how many pounds is this in a gram? Well, first of all, what do I want to do? I've got way over here on the left. So this is what we begin with. We've got pounds. Way over here on the right, I want gallons. How do I get from pounds to gallons? I'm going to go from pounds to what? You tell me. What do I go to? Grams. Let's go to grams, right? Because I know what about water?
It's 1 milliliter.
Density. Yeah, the density of water is a gram per milliliter. So I want to get out of pounds and go to grams. And then I want to use the density, which gets me to milliliters. And then I want to go to liters, probably, which then I can go to gallons. You see the path? That's the trickiest part about chemistry when we get into the math of things, is to know the path I need to take to get to the final result. So we begin with the end in mind. We want to go to gallons, and we start with pounds. And so we got to go somehow through this path. So let's just build up the conversion factors. This is a little bit harder than the one on the test, okay? But not totally unreasonable. So 10,000 pounds. So 1 pound is 454 grams. I got a really funny story about that, but I'll tell you later. Okay. And then I want to get out of grams and into milliliters, and I can use water for that. And I know the density of water is 1 gram per milliliter, but I'm not going to write that here, 1 gram on top per milliliter on bottom, because it'll be upside down. I need the gram on bottom. So it's 1 gram per milliliter. Those two things are equal. When we say the density of water tells us 1 gram of water is equal to 1 milliliter, I can write it whichever way I want because the top equals the bottom. So I can write it upside down and it doesn't make any problems for me. I use it as a conversion factor. So now I'm in milliliters. How many milliliters are in a liter? 1,000. Let's go ahead and use the milli as it's supposed to be. So 10 to the minus 3 is milli. So milliliter on bottom, liter on top. That's the same as writing 1,000 milliliters on bottom. That'd be 10 to the minus 3 on top. So I'm out of milliliters and into liters. And now I need to know how many liters are in a gallon. I think it's 3.78. Yeah, 3.78. I was going to look it up. So the last one is 3.78 liters per gallon. So I've done it. Now, if you're doing this on your calculator and you see that 10 to the minus 3, that's where you're going to screw it up. So when you see 10 to the minus 3, you can divide by 1,000. Okay? Because that's probably less prone to error than you're trying to figure out how to multiply by 10 to the minus 3. But anyway, so we'll take out our calculators. $10,000, 454, and 1,000 divide, and 3.78 divide. So it's gonna work. As far as significant figures, I don't know. I mean, 10,000, do I mean 10,000 to the ones place, or do I have really one significant figure? I'm not going to worry about sig figs on this one. So 1,201 gallons. Okay.
So would it technically be then just like 1,000 gallons?
Yeah, you could say 1,000 gallons if you just wanted to just keep one sig fig as an estimate. You'd say, yeah, 10,000 pound ship displaces 1,000 gallons. Yeah, just seems kind of low to me.
It does seem really small.
Yeah.
How'd you get the 454 grams?
That's the mass of a pound. Yeah.
Oh, you're gonna give us those conversions.
Yes, so you would have gotten this one. I've actually told you in the problem that the density of water is 1 gram per mil, but
Okay.
it's still something you should memorize. This one you're not getting.
Right.
You have to know the metric system. And this one I would give you. Yeah. Yeah, check this one. I think it's, let me see, I think I got it on.
I got the same.
Yeah, got it. Yeah, 3.785. Yeah. Okay. Now I know that a gallon weighs about 8 pounds, so if we took 10,000, yeah, 1250. So that checks out. Cool. So that's how using. Someone said something to begin us down this road was using density as a conversion factor. So see, all we did was convert units. We just converted pounds to pounds to gallons of water, and we had to use the density because whenever you're going from a mass to a volume, you need to know the density of the substance. Yes.
And then, for the 10.3, I think it's called C, the psi prefixes or something on the outs. Yeah, the SI.
Yeah, SI. So SI is a French phrase, System International. So when we talk about the International System of Units, that's what SI is.
So, which ones would we need to memorize?
It's best to go. I mean, eventually, I want you to work up to plus and minus 10 to the 18. So that goes from exa all the way down to atto. But for this, I'd be happy if you had plus and minus 6. So plus 6 would be mega. So mega, kilo, mega, kilo, hectodeca, and then you have the meter, and then you have deci, centi, milli, micro.
But overall, you said 10 to negative 18?
Yes. Because once you get below micro, then you have nano, pico, femto, atto. And so then once you're going by threes there, so then that would be 10 to the minus 9, minus 12, minus 15. Yeah, so maybe that's only down to the 10 to the minus 15. Yes?
I'm not sure if you already said this, but are there any questions covering energy?
No, the kinetic energy was just thrown in there just as a one that had a combination unit, right? Like in terms of energy, joules of being a kilogram meter squared per second squared, and I wanted you guys just to work a problem with that kind of combination of units. Yeah. It's kind of a random question type thrown in there. Yeah. Good. Yes.
A little bit more clarification when it comes to when we decide our final answer. Will it tell us to make sure to put it in sig fig?
The sig fig problems are super obvious. There's 4 of them. All the other problems, the answer, since it's multiple choice, none of them are within a sig fig of each other. You know what I'm saying? Let me just check that statement. Okay. Yeah. So of the unit conversion ones, there's no way to miss those by just messing up the sig figs, right? So the answers are far enough apart that you won't have like a 2.4 and a 2.46 and a 2.3, where they're all within, say, maybe a rounding error or whatever. But on the 4 significant ones, it's like, the answers are testing your sig fig knowledge. And so they would all be right if you rounded a different way. So you got to round the correct way to get it right. Yeah. It's interesting the sig figs, because it's in this course the first really detailed analysis. It seems like we really emphasize it a lot, but later on when you get to quantitative analysis, instrumental analysis, and PChem, we have a different way of determining where our uncertainty lies. We do the experiment more than one time, and that tells us where to round. So the sig figs seem super important at this part of the course, But later on, they become less important because we have other ways of estimating our uncertainty. So think about, that's really what the sig fig thing is about, is where are you uncertain? If I have a 4-place balance, I'm measuring out 4 decimal places. That last decimal place is where I'm uncertain, right? According to the sig fig convention. But if I measure the same thing 3 times and it changes in the second decimal place, so I've measured the same object, some kind of water sample or something, measure it 3 times. Even though I'm measuring the 4 digits, it's changing in the second digit. So the second digit is where the uncertainty lies. Every time I measure this object, the first digit's the same. Second digit's all over the place. Third digit's ridiculous, and the fourth digit I don't care about. Because that's where my uncertainty is in the second digit. That's what we'll do in quant, instrumental analysis, CHEM, and so on. But at this level, we got to teach you about uncertainty some way, and that's what that significant figure convention is. So if you have not done the experiment multiple times, all you can say is I measured to 4 decimal places, therefore I'm uncertain in that 4th decimal place. So it's sort of feels like it's overemphasized to me because y'all get stressed about it because it's pretty particular, and then because of your stress, it makes it feel like this is the most important thing in science. It's not. Okay, so that's why I only asked like 3 or 4 questions on it. Pretty straightforward rules, but pretty tedious questions. Okay, next question. Yes. Oh, good question. This kind right here. So it's the long skinny one. It doesn't have to be green, it can be blue. And there's some places that give out free ones, but you can buy a pack for pretty inexpensive at the bookstore. There's anybody know where there's some free ones? There's some places on campus. That still gives them out.
If you go by the Alumni Association office.
Yeah.
On 75.
Okay.
For free.
Okay, that's cool.
If
Yeah.
you're like veteran affiliated, the Veterans Resource Center also gives those out.
Okay.
And the thrift store.
That's awesome. Yeah, so, but even if you want to like go in and pay real cash money for them, they're not that expensive. Just go to the bookstore and get a pack of 10. Yeah, $3.99. But it all helps, right? I would say that's a burrito at Taco Bell, but it's not a burrito anymore. That used to be my go-to for a $5 lunch. Now it's $13. Anyway, yeah, 2 burrito supremes and a Coke. Yeah, that's good. Yeah. Facts. Yeah. All right, who else? Question.
Can you go over the rules for like the eights when you go up so
Yeah.
many and when you go down so many?
Yeah. So I've memorized the chlorates. So chlorate. So this, let me do over here. So that's ClO. Do you know it? 3. Very good. And how many minuses? Just 1. So that's chlorate. So that's the one I've got memorized. And then from there, I go down and I go up. What do you want to do first, up or down?
Well, there's only one up, right?
Right. Let's go up then. So you can only put 1 more oxygen on there. So ClO4. What, does the charge change?
No.
Correct. So that's perchlorate. And then now let's go down. ClO2, same minus. What do we do to the word? Chloride. Okay, and then ClO minus hypochlorite. Okay, so this is the model, and it works for all of the halogens. So what if I had FO4 minus perfluorate. So you see, once you memorize 1, then you just apply the same thing to all of those. If it was IO4 minus, per iodate. Yeah. So you don't have to memorize everything on the periodic table, but you have these classes of groups. Now, what if I had so I like to, again, memorize the 8s. So what is NO3 minus? Nitrate. And so then the only other one we have is nitrite. Why it doesn't have it's just not big enough. The add nitrogen is not big enough to have a per nitrate. But what about the, let me erase these. We're kind of running short on time, so I'm going to try to hurry. SO4 2 minus.
Sulfate.
That's sulfate. So the SO4 one is sulfate, not persulfate. But if that's the 8, then if I subtract 1 oxygen, then it's sulfite. So it's just learn the 8s, and then when you subtract an oxygen, then you have the ites. So if you memorize chlorate, nitrate, sulfate, carbonate, then you know the 8s, and then you can go down and up in each of those groups. But it's tricky because sulfate is SO4, chlorate is ClO3. That's the one thing that people can mess up, I think, in that. Yes?
Whenever you go up, is there another like you know how you went up on chlorate and it became perchlorate?
Mm-hmm.
Is there another like name for another one that if it like goes up anymore?
No. Mm-hmm. Yeah, it stops
So it's
there.
always gonna be perchlorate?
Yeah, that's where it stops. Mm-hmm. Yep. And then know how to make the acids out of these, right? So chlorate would be chloric acid. Sulfite would be chlorus acid. And then hypochlorite would be hypochlorus acid. So ites always go away and us's come in.
And that's adding a hydrogen to the front.
And adding hydrogen to the front, yeah. Technically a proton to cancel out the negative
And
charge.
so if it's like, hydrogen for us acid, it would be H2SO3 because of the 2 minus on.
You said fluor, but I think it means sulfur, yeah. Hydros, it would just be sulfurous acid. We put that extra UR for sulfur.
But writing it out, it would be H2SO3.
Yeah, H2SO3, yeah. Yeah. And sulfuric acid would be H2SO4, yeah. All right, guys, I think you're well prepared. You're gonna do great. Okay, talk to you later.